graph that relate the chain of resistance to temperature. Like in this case, the principle is as the temperature goes down, if it goes up, resistance goes down. Sorry, temperature goes down, resistance goes down. So resistance high, temperature high. As resistance goes down, temperature become higher, right? Which means compared to platinum earlier, platinum is the opposite. As the resistance goes up, temperature goes up. So it come together. Temperature goes up, resistance goes up. But for thermistor, it's the opposite. Resistance goes down, temperature goes up. And it can measure up to 2-3 decimal. That's the importance of using thermistor. It can measure, say, for example, 37.0001. So 2-3 decimal. So slight change in body temperature it can detect. Let's say you want to measure cardiac output using PA catheter. Gold standard PA catheter to measure cardiac output. So you inject 10 ml of normal saline at room temperature. So when it enters the PA, in the pulmonary artery, the blood temperature is 37. You are injecting room temperature normal saline. So 23 plus 37. So the change will be maybe 36.90, it dropped very little. Blood temperature 37, saline 23. So it mixes, right, in the blood. One cycle, temperature at that particular point, maybe 36.970, 2 decimal, or 977. So you can pick up small change in the blood temperature by injecting normal saline at room temperature, right? So you can detect up to 2 or 3 decimal temperature change. That's the beauty of thermistor. So, okay. Now, thermocouple. This is used to measure your yogurt, for example. Yogurt, your beer, soya bean, or Coca-Cola. Because they manufacture this in the factory, right? Big factory, they have 10 gallon, 1,000 liter of Coca-Cola. To make it clean, no fungal growth, no bacterial, they have to keep it at certain temperature. Yogurt, for example. Okay? So they use thermocouple to measure, this is the temperature I want, this is the temperature I want for my yogurt. So it will be better, taste nicer. So they use thermocouple. You want a good beer, use thermocouple, not thermistor, thermocouple. So because it is like a probe, they dip into this yogurt solution, temperature 23. Yeah, this is the one I want, temperature 23. Because it gives you an accurate measurement of the temperature of that yogurt, for example. Right? So just keep in mind, let's say you go to the volcanic area, you cannot use thermistor, you cannot use thermocouple. You use infrared temperature detector. So you are, say, 100 meters from the volcanic area. You get the infrared thermometer, you measure it. Temperature at that point, 1000 degrees Celsius, something like that. Right? So for our purposes, we use thermistor. So thermistor will determine our core body temperature. For example, you use your nasopharyngeal temperature probe, right? You put into the nasopharyngeal, or you can use TM temperature probe, or you use rectal temperature probe. You measure the core body temperature, indicate the temperature in the blood, the core, in the blood, or in the brain. So this is core body temperature. Not the shell. The shell is just below the skin, at or below the skin. Deeper to that is the intermediate zone. So what we want to know is the core body temperature. Technically, we use thermistor temperature probe. Right? The one we use is thermistor. In the OT is thermistor, nasopharyngeal temperature probe using thermistor technique. Right. So thermistor is made from a small bit of heavy metal, for example, manganese, molybdenum. Right. This is not purely part 1, but if you know, it's better lah, in case they ask you in the exam. Okay. Now, when you're anesthesizing a small baby, neonates, elderly patient, so the temperature probe is important. So you use your thermistor nasopharyngeal temperature probe to monitor the body temperature, because if you expose the neonates elderly, you don't cover the body. So most of the time, the heat loss is by radiation. This is important. Radiation. Radiation is the main mechanism of heat loss in the exposed skin. That's why in neonates, infants, babies, you have to cover them to prevent hypothermia, because the heat loss is mainly by radiation. Second, convection. So to know exactly the amount of heat loss or the amount of body temperature, you use thermistor temperature probe. Ideally, let's say you put the thermistor temperature probe in the larynx, it's not 100% accurate, even though it is near to the brainstem, right? You put TM, also not 100% accurate. The best is to put the probe into the blood. How do you do it? Yeah, you use this floating temperature probe. You insert through the femoral vein. So when we do DHCA, deep hypothermic circulatory arrest, DHCA, which we have done two cases, I think. So we monitor the core body temperature by inserting a thermistor probe into the IVC to get the exact body temperature to keep the brain working, functioning. So we drop the body temperature up to 2018. Right? So you understand? So we put the thermistor probe into the IVC, measure the actual core body temperature, the temperature of the blood. So the thermistor is the best device to measure the core body temperature by inserting a temperature probe into the IVC via femoral vein. Then you are measuring the core body temperature, so you can drop the body temperature to 18 to protect the brain during deep hypothermic circulatory arrest for certain surgery. For example, aortic surgery, ascending aorta surgery, descending aorta, kan? Have you done that? You heard about that? This is what we want as a final year student. At least you have some idea lah. You cannot put the probe into the brain, kan? Nearest TM not as great as the one you put in the blood, right? Okay. No, I skip that one. Need hand? I will go to monitoring. Okay. This is important. The capnogram, basically, you measure the entire CO2 by using infrared analyzer, right? Which means this is your gas sample, gas sample sini masuk sini. So, sorry, ini sample, your expired gas goes this way into this chamber, right? This is reference chamber, this one sample chamber. You inject your CO2, your expired gas. CO2 will absorb infrared. This infrared source is from infrared light source coming from hot wire with certain frequency. So CO2 will absorb this certain frequency of infrared, resulting in reduced intensity of the infrared, which is detected here. So the amount of CO2 can be calculated lah. They get the ratio between sample chamber and reference chamber. Then the amount of CO2 is calculated simply because CO2 here will absorb infrared, and we measure the intensity of infrared. Then we compare with the reference. So this is the principle, side. So you have to know the principle only. Now, the one we are using in the OT is the side sampling system. Side stream. Side stream sampling, which means there's a sample line from the Y-piece, right, to the CO2 module. So that is about how many meters? About that? 1 meter, about 1 meter. Sampling line attached to the Y-piece to the CO2 module in the machine, and it will analyze the CO2 content in that specific gas using infrared analyzer. So then, because of the long tubing, it get a slow response to get the capnograph. After you have intubated the patient, right, it takes maybe 30 seconds to get the waveform, right? So there's a slow response using this technique. If you use the mainstream of the capnograph, you get the response of CO2 immediately, right? So the mainstream, this is the mainstream. This mainstream, which means the CO2 analyzer is attached to the patient at the Y-piece. It's sitting there, right? So it will analyze there and there without using sampling line. So the response is within 5 seconds you get the CO2 waveform already. So this is the difference between side stream and central stream. Okay, mainstream, side stream and mainstream. So what you get from this technique, either side stream or mainstream, in terms of response, maybe we don't bother very much, because what is the difference between 5 seconds and 30 seconds, right? Patient won't die because of 30 seconds. So you can still get capnograph 30 seconds later compared to 5 seconds. So this is what you get. You have A, B, C, D, aspiration, inspiration. You should be able to draw this diagram and interpret the phases, right? It is not part 1, this is part 2 now. This is applied clinical measurement. So the measurement of the CO2, as you see from here, 0 CO2 because of inspiration. Let's say you get FiCO2 5 millimeter mercury, which means it's a rebreathing in the circuit, right? You have to change the soda lime, right? It should be 0. FiCO2 should be 0. So this is the end-tidal CO2, mean of 40. How do you measure it? You measure it here. Not along this way, but at the end of expiration, before beginning of inspiration. So this is the measurement you take for end-tidal CO2. If I were to draw this diagram, then I want you to point where is the end-tidal CO2. You get it wrong, you come back in 6 months. Because this is very important, simple. Very simple, important. Have to, when you want to teach MO, you must know to give the right information. Now, there are few pictures or scenarios whereby CO2 waveform will have different pattern, which I think you should know. For example, like this, the capnograph waveform, as it goes down, become smaller. So what does it mean? It can be hypotension, right? It can be impending cardiac arrest, but it's not cardiac arrest, impending cardiac arrest, hypotension, or hypovolemia. So you should be able to interpret diagram like this. So let's say the waveform is not typically square, right? It is bit slant. The takeoff is bit slow like that. You see in the monitor, in your display monitor. Then it means there is some airway obstruction. The patient is having difficulty to exhale the gas during expiration. So this is typical capnograph waveform in asthmatic or bronchospasm, macam tu. Right? Then you should be able to interpret. Kalau tak, you have to come back 6 months. Or you need another 6 months training lah. So you lose how many thousand in 6 months? Oh, yeah, a lot dah, tak money ah. Specialist allowed 1,500 times 6. So if tengok money, you think of passing the exam. Okay, this is typical waveform of impending cardiac arrest or maybe embolism. The trend is declining slowly, kan? So as the time goes, it becomes smaller. Eventually, kalau arrested, it flat lah. So normal capnograph, hyperventilation, right? Hypoventilation, CO2 more than 40, right? Bronchospasm I mentioned earlier, a bit slanted there, right? Okay, so these are the 3 typical waveform that you should be able to interpret. If I give you this diagram, you should be interpret within 30 seconds, maybe less. Now, what about pulse oximeter? Pulse oximeter is a device that measures the oxygen saturation in the capillary blood. So, you know this diagram? Do you know the amount of oxyhemoglobin, deoxyhemoglobin absorption at different wavelength? So, they calculated the differences between oxyhemoglobin, deoxyhemoglobin absorption at different wavelength, IR wavelength. You want to know the detail? I give you the detail, which is very complicated. All this formula, and then you get the actual SpO2 based on 2 formulas, right? What is the formulas? BS and Lambert. Okay. So you get the measurement of SpO2 97 and below. So basically, this is the 2 diode, red and infrared, that a source for red and infrared radiation waveform at different wavelength. Then photocell to detect these 2 different infrared, red and infrared, and then electronic processes that based on these 2 formulas you get this arterial waveform. Now, this is the detail. Now, the limitation. These are the limitation that you get inaccurate SpO2 measurement. For example, carboxyhemoglobin, you get falsely high. For example, you use nail polish, weak signal, right? You might get low measurement. What else? Made hemoglobin, it can be low and high measurement. Weak arterial pulsation, low measurement. Or peripheral vasoconstriction, low measurement. So, okay. No. So it is a standard monitor, capnograph, and SpO2. In fact, now they have included in Australia the ultrasound. It's a standard device, machine that you use before cannulation ataupun block. So, pulse oximeter, capnograph, now ultrasound. Besides ECG and other thing lah. So ultrasound is a must. Without that, they can prosecute in case of complication. Let's say you are cannulating the IGV, internal jugular vein, or you're performing femoral nerve block without ultrasound and end up with hematoma or embolism. They sue you because you don't use ultrasound. So now it has come to that level. You cannot perform regional without ultrasound, except central block. Other block you must use ultrasound. Even cannulation, outline cannulation, you cannot simply poke like that. Ultrasound in Australia. So if thing happen, complication, they look back at your notes. Do you use ultrasound? No. You go to the court. So now, same as measuring oxygen in the blood. Just now SpO2, you measure oxygen saturation in the capillary blood. Now you want to measure oxygen in the blood, you use ABG machine, right? So basically, you get the outline, arterial blood from your outline, sent to ABG machine. ABG will interpret, you get the PaO2, how much, right? From PaO2, you can calculate SpO2. So basically, the device they use is oxygen electrode. So you don't have to know detail. The oxygen electrode is also called Clark electrode or polarographic electrode. That's it. So if in the MCQ they ask you, the device, machine, equipment used to measure oxygen in the blood, this is the equipment. Right? If they ask you, what is the instrument, equipment used to measure oxygen in the gas mixture, fuel cell or galvanic cell. The detail is part 1. So you cannot forget your part 1. This is to measure oxygen in the blood, you use Clark electrode. If you want distinction, you write down this one, you get A+. You dapat Asmoron Award. Asmoron Award lah. This the detail lah. Now, let's say you want to measure certain gases in the gas mixture. You want to measure 20 gases in the gas mixture. You don't want to measure oxygen only, you want to measure oxygen, nitrogen, CO2, nitrous, carbon monoxide, everything in one measurement. You use mass spectrometer. This is used in the factory, right? So they want to measure 10 gases in one gas sample gas, kan? They want to know oxygen, nitrogen, N2O, what else? CO, sulfur, chlorine, everything. So they use mass spectrometer. We will measure multiple gases at one time. So we don't use for anesthetic because anesthetic we want to measure oxygen only or CO2 only. But this machine can measure 20 gases, 30 gases. So, but this is the machine you can use to measure oxygen. Besides fuel cell, you can use this, right? For blood, Clark electrode, right? Remember that? Many of you confused between how do you measure oxygen in the blood, how do you measure oxygen in gas mixture. Almost all get confused. Then you lose 1 mark. 1 mark can make a big difference. This is the mass cell based on the molecular weight of the gas. The heavier the gas, there will be least deflection after the magnet. The lighter the gas, it will be most deflected. For example, this is mass spectrometer. Oxygen 32, molecular weight 32, CO2 44. So oxygen will be more deflected compared to nitrous oxide or CO2, right? So as simple as that. Then they calibrate lah. The set for oxygen is 32, CO2 44. Then they calibrate accordingly. So if the molecule of the gas fall at this spot, is belong to CO2 because molecular weight 44, oxygen 32. Then they get say 10 measurement, 20 measurement at the same setting, same time. But it's not meant for anesthesia. Okay, this is for ICU. ICU important because for ICU ventilator, they use many paramagnetic oxygen analyzer. So which means the FiO2 measured by the ventilator, Drager ke, Hamilton ke, whatever ventilator use, they use paramagnetic oxygen analyzer to measure the Fi oxygen delivered by you. So then they don't use fuel cell, they don't use mass spectrometer, they use paramagnetic oxygen analyzer based on the paramagnetic property of the gas. You just mentioned a paramagnetic oxygen analyzer for ICU ventilator. Okay lah. So detail maybe you draw this diagram, you are superhero lah. Okay, next now we tend to forget about important measurement, even though you have Sugamadak, though you have Sugamadak, but it's also important for you to measure the degree of relaxation by using gold standard equipment which is a nerve stimulator, right? Many of us have forgotten. But if you work in a small hospital, you are the specialist there, and you are given some money. You want to buy good JM machine, you good monitor, what else? Other things. Then ultrasound, yes, fine. This one only cost about 10,000. Example of nerve stimulator, sponsored by Tracurium. Fisher Fickle, okay. Now, this nerve stimulator, the different brand, but they are the same. Okay. Now you are thinking where to put the electrodes, kan? Which one positive, which one negative? It's always mingling in your mind. I don't know which one positive, proximal, distal. This is the one I show you. So positive is proximal. Positive, proximal, negative, distal. Remember, positive atas lah. Positive, negative. And then this is the sensor detector to detect the movement of the adductor pollicis muscle, the thumb, right? Okay. Right there. So, positive, negative. Merah always positive. You go to wiring pun merah positive, right? Positive, positive. Positive, negative. Then this one they put sensors in lah. Apa tu ada? Okay. One missing, dia tak ada sensors itu. Okay. Now, how do you monitor? You have two modes lah. Number one is train of 4, count, TOFC, right? You count lah the number of twitches. 1, 2, 3, 4. Count the twitches. Number 2, you calculate the ratio. The fourth to number 1. The fourth count T4 against T1. So let's say no block. You must set the system before you give your relaxant, right? It's no point giving relaxant then you set up the system. No point. You must get the supramaximal current. Supramaximal current means the minimum current to stimulate the muscle. Maknanya you increase from 0, 1, 2, 3, 4 sampai to about 20, you get single twitch. That is the minimum current to initiate twitch movement of the thumb. Supramaximal. Normally about 20, depending on the skin layer lah. If you are thin, maybe 15 you get the twitch, right? Single twitch. If you're fat, maybe you need 40 because of skin resistance, right? So about 20, 25 average. So single twitch, you increase the current, got one twitch, that's supramaximal current. And then you change the knob from single to train of 4, count and ratio. No paralysis, you get 4. 1, 2, 3, 4. 4 count, eh? So no paralysis, no rock. You bagi sat simultaneum, let's say normal macam tu. Sat 4 count, same height but weaker count. So this is sat simultaneum, right? This is rocuronium. So this is before sat. This is sat given. This is no sat, no rock. This is with rock. You get fade. You give rock, fade. Number 3, 1, 2, 1, 2, 3, 4. This is not complete paralysis in partial. So you count the number of twitches. 1, 2, 3, 4. Maknanya there's a fade. It's a fade phenomenon. Fade phenomenon for rocuronium. There's no fade phenomenon for sat simultaneum. There's no change in the height of the twitch if you don't give any muscle relaxation. Now back to ratio. Ratio, you take twitch number 4 against twitch number 1 ratio. So when you look at the monitor, you get TOF count. How many count? Ratio. In order to get ratio, you must have 4 count. Because you are measuring the fourth against 1. So in order to get ratio, there must be 4 count. So ratio is important when to reverse. Right? When to reverse, you get TOFR. TOFR. Count you want to make sure he's completely paralyzed, right? Count 0, completely paralyzed, you can intubate. Count 0, you still get the ratio, you cannot intubate, right? You want to reverse with nestametropine, you must get the ratio, which means the count already 4, but ratio can be 0.95, can be 0.75, can be 6. You faham that? This is important. Many of you can answer this. All right? Even though this is look like part 1, but in the final they do ask in the oral exam. Maybe one day they ask in the SQ. Okay. Now we have Sugamadek, yeah? Sugamadek. Okay. I just go a bit detailed. No block for count, right? Right, no block. Complete for same height lah. Moderate block count 1 or 0 to 1 moderate block. Kalau deep block memang 0 lah, complete 0 Right. This is just for intense relaxation. For certain surgery, you make sure count 0, PTC pun 0, right? Okay. This is the detail. Detail maybe I don't want to go through because there are other things that I want to tell you. Base. Oh, this is respiratory index monitoring. You are familiar with this diagram, kan? You know BIS monitor, and then you look at the score, 0 to 100. 100 mean patient is fully awake. 0 is dead. Sudah. Flat EEG. So the principle of BIS is basically referring to the activity of the EEG. There are 4 EEG waveform. Anybody knows? Okay. Maybe I don't. Okay. Okay. So when we are awake, the BIS is 0, is 100%, 90 and above lah. Alright. So the activity is mainly due to beta, beta waveform, which means high amplitude, high frequency, right? So awake. When you want to perform or you want to provide MAC for colonoscopy, then you must have BIS around 70, 70, 60, moderate sedation, right? Now the anesthetic ratio in Malaysia, we finish 1 o'clock. 1. Okay. The ratio NS to population 1 in 30,000. 1 NS for 30 population, which is very very low lah compared to Australia 1 to 10. 1 to 10,000.
Kejap. 1 to 10.
Ours 1 to 30, Australia 1 to 10,000, UK 1 to 8,000, which means we still need anesthesiologists for the country, excluding MAC, because the physician surgeon want us to provide MAC. Therefore, the ratio has gone up to 140, 1 to 40,000. So anesthetist is no longer working in the OT ICU, but they want us to work in the endoscopic suite because they want us to provide MAC for colonoscopy, bronchoscopy, anything. So that's why this is important for us to know. So you must have BIS monitor when you're performing MAC in the endoscopic suite. Make sure you're giving the correct dose of remifentanil, methoxsalen, whatever lah. So intra-op, you want BIS around 40, 50, around here lah. So the waveform ni based on EEG activity, remember? So this is the score that we want, and the placement though, I want to show you. Where's the placement though? This is straightforward lah, placement. The next one is the evoked potential. This is not new because we've been doing TIVA for neurosurgery, for cochlear transplant, and other orthopedic spinal cord surgery. So you have to know what is evoked potential. Okay. Basically, there are two types of evoked potential. I just want to simplify it. One, the sensory evoked potential. Number two, motor evoked potential. Right. So the best is to use both mode during orthopedic neurosurgery. You use sensory and motor. Now, the sensory is called SSEP. SSEP. Somatosensory evoked potential. It can be visual, auditory. These are sensory lah. BAAP, brainstem, auditory evoked potential. Boleh pakai. SSAP, sensory, SSAP. This SSAP. Okay, you can use BAAP or SSAP without MEP. Alright. So basically, you can also use motor MEP alone boleh, depending on the surgeon lah. Like orthopedic surgeon, UKM, they like to use MEP alone, not SSEP. Right? Okay, so basically what happened at the molecular level kan? Let's say you give local anesthetic, you block the nerve conduction at the level of depolarization, betul? You give relaxant, you block depolarization. There's no action potential, you block the nerve conduction, right? Okay. If you give, so you monitor the TOF count, TOF ratio lah, right? Because you give muscle relaxant, no action potential, no nerve conduction, you block nerve conduction. Therefore, you know the twitches, no twitches, there's no nerve conduction. You give local anesthetic. Sorry, I rephrase. Let's say you give muscle relaxant, it block the channel, ACH channel. They compete with ACH. There's no action potential, there's no depolarization, there's no nerve conduction. Okay? You give local anesthetic, it block the nerve conduction, right? By preventing action potential. Two different kan? Relaxant block the receptor, prevent action potential conduction. Local, they block the sodium channel receptor, right? A bit higher lah, up higher lah. Motor evoked potential, it prevent, we detect that process. We detect not the contraction or paralysis, detect at that molecular level, at the action potential, it detect there. It detect, which means it is more higher lah at the molecular level kan. So you detect the present absence of action potential. This is MEP lah. MEP is to detect the absence or presence of action potential. So in order to measure that, you have to put electrode near the cortex lah, cortex. So I don't know the detail lah, but by analyzing the waveform, they can detect whether there is action potential or no action potential. They detect. The form look like this example kan. So let's say there's an orthopedic surgeon, they cut the motor neuron. Before they cut, they touch lah. I want to cut or not? Is it vessel, nerve, tendon? So if they see the patient is not paralyzed, right? If there is a conduction, there is exponential, there is a nerve for the nerve. So they don't cut. If it is blood vessel, there's no exponential, they don't cut. So as simple as that. So that's why you need a technician to interpret the action potential punya waveform. We do not know kan, and that's tak tahu. Cuma what is important for us, you must use SSEP, BAP or MAP or both or all three to make sure the patient is apneic, not paralyzed, apneic, and allow surgeon to operate. Therefore, they can know this is nerve, this is not nerve. If you give relaxant, everything will be paralyzed. The surgeon wouldn't know this is nerve, blood vessel, they cut. That's the reason why they use MEP, SSEP, or BAP during neurosurgery or orthopedic surgery. you can read this later. I give you the detail. I think before I just quickly go to ECG, I think you're straightforward, that issue. In terms of unipolar, bipolar. Unipolar referring to the chest lead, right? V1 to V6 unipolar. Bipolar referring to two leads. Lead 1, 2, 3, AVL, AVF, AVR, which means we are measuring two poles, right, left, apex. The vector this way, this way, this way. So it forms a triangle called interval triangle. So the vector, the direction of current, all towards the heart, this way, this way, this way, all towards the heart, apex of the heart. So the vector, so these three vectors meet together to form a interval triangle. So these three vectors are formed through bipolar leads, 1, 2, 3, AVL, AVF, AVR. Unipolar, many chest lead to indicate the surface activity of the heart. So, for example, V1, V2, mainly reflecting the anterior chamber of the heart, anterior surface of the heart. Right? 3, 4, septum, 5, 6, lateral. Right? Let's say you have anteroseptal infarct. Then V1 to V6 changes. They will be changing anteroseptal, extensive anteroseptal infarct. You get changes from V1 to V6, right? Which means affect the whole surface of the heart, anterior, septum, and lateral. Kalau 5, 6, lateral infarct. Anterior, V1, V2. So if patient is in cardiogenic shock, which means it affecting either anterolateral or lateral, right? Cardiogenic shock, normally anterolateral, the whole anterior septum, lateral, which means affect the LAD, the left main stem, right? If just lateral, patient might have APO, left ventricular failure, not in shock, maybe just hypotension. Kalau anterolateral, patient in cardiac shock, collapse, and they normally die before arrival to the hospital. Right? No. To know the characteristic of ST changes, so I think you all know. For example, the acute phase will not appear immediately. The acute phase of ST changes will appear maybe 5 hours later. The patient is already in shock. You have to do CPR. But ECG changes might be very minimum, ST elevation minimum, right? Maybe minimum 2, 3 mm above or below. In fact, normally above. Ischemia below, more than 2 mm. But the full-blown changes will be seen 5 hours later with Q wave, which means the appearance of Q wave will be seen 5, 6 hours later, not immediately. You may see ST elevation without Q, but 5 hours later, you get deep Q plus ST elevation. That indicate infarct. Infarct means the muscle, dead muscle. Dead muscle, there's no conduction. Therefore, that's why the ECG itu naik atas, then elevated, because there's no nerve conduction through the dead tissue, infarcted myocardium. So this is a typical acute infarct, ST elevation more than 2 mm, the full-blown, full evolved phase. And here you can see acute inferior, and inferior is diagnosed by using bipolar 2-3 AVF. Inferior, because inferior, you cannot detect or look the inferior surface of the heart by using trans echo. Tak boleh. You have to use transesophageal. So as it is not as important as anterior or anterolateral, therefore it is difficult to detect by using unipolar. If you use unipolar, you cannot detect inferior infarct because you need 12 lead. Or even modified CM5 pun you cannot detect inferior. CM5. CM5 kan? Modified CM5 you can detect anterolateral, anteroseptal, but inferior you have to use 12 lead ECG. After all, infrared infarct is not detrimental as anterolateral, causing acute left ventricular failure and shock. Infrared infarct may be detrimental if there is significant AV conduction abnormalities. For example, because infrared infarct ini basically area is supplied by RCA, which also supply the SNO. So those with infrared infarct, they will develop arrhythmia. Depending on the type, if develop severe SVT, they die lah. Unless you do defib kan. They normally don't die because you have time to treat. You got infrared infarct, you get ST no ST changes, but you minimum ST changes 2-3 AVF, but you get maybe AV block, a bit of SVT, tachycardia, more rhythm abnormalities. So infrared infarct is not as detrimental as anterolateral infarct causing cardiogenic shock. So they don't die there and there. Kan? You have time to treat lah arrhythmia. You give whatever you want, amiodarone ke anti-arrhythmic drug kan. Because the heart is not failing, that the rhythm is failing. Itu je infrared infarct. Okay. So in the exam, we can give you a piece of paper, piece of paper to interpret. For example, this is the piece of paper in front of you. During the medical evaluation, what is your diagnosis? Depend lah. Let's say, tell me what are the abnormalities in this ECG. Then you tell us one by one. If I ask you, what is your diagnosis? You go straight to AF. Don't waste time. PR interval, QRS, RR. This is AF. No. If you ask you, what is your diagnosis? Straight away AF. If you ask you describe this ECG, start one by one. Okay, this is the way. Okay, I skip. No, I think I skip this one. I just show you. Oh, echo. No echo. No echo. If you're doing cardiac anesthesia, you have to learn echo. Echo. Not only trans-echo but trans-esophageal, because echo is actually important for general anesthetists and ED physician nowadays. ED physician are learning echo now from us, from anesthesiology, from cardiac anesthetists. Not many cardiac NS are well off or know very well about echo, kan? General anesthetists, but cardiac they are very good. Cardiac anesthetists they learn. Some of them have diploma in echo. So actually not difficult to learn. This is a matter of like doing ultrasound for femoral block, ultrasound for internal jugular vein cannulation. The same. So what you see here, the chambers, transthoracic. You see just like doing block for sciatic nerve block. You see all layers. Even more difficult to get the sciatic nerve block. Why the nerve? This is straightforward. You put the ultrasound on the chest, transthoracic. Then you see all the chambers. Then you study the anatomy of the chambers. So, from echo, you can see the anatomy. You see right chambers, left chambers. RA, LA, RV, LV. Anatomy, kan? Then you know the valve. So, information you get from transesophageal, transthoracic or transesophageal, number one, anatomy, landmark, anatomy of the heart. Anatomy, chambers, RA, LA, RV, LV. You see the valve, right? Normal tak normal. You see the septum. Ada hole tak ada hole. ASD, VSD, valve, MS, all those things. Calcification, vegetation. All these are the anatomical landmark that you can see there and there. Right? There's no formula, no calculation. You see there and there. When they ask you, what are the information you can obtain from doing trans-echo? I see all the chambers. Number two, I can see the valve. I can see calcification, vegetation. I can see the septum, normal tak normal. I can see the contraction, the nature of contraction. These are direct measurement. Okay. So, example, this one. You see all these chambers, tak ada masalah. The bigger chambers, you see RA, right? Okay. This one the 3D, okay. Below ni 3D. So, detail. Okay. What I want to stress is about the anatomy, you know lah. But the contraction of the myocardium, this is a bit difficult to interpret. To know, you must do echo on the normal heart first. Then you can appreciate the muscle contraction. You do routine ni lah, you curi-curi ke apa-apa di ICU tu kan. You ask your specialist, or he's also learning doing echo, you do it. This is the nature. How does it look? RA, like this, contraction. You learn from the normal heart first, then you know the abnormal heart. So in normal heart, you get the normal contraction, right? Contraction. So, let's say you wouldn't know hypokinetic ataupun hypokinesia unless you know the normal contraction. You can appreciate. Hypokinesia means decrease in the myocardium contraction. There's a contraction normal actually. Any weaker contraction is called hypokinesia. Right? Hypokinesia. Alright. Let's say contraction normal like that. Abnormal, weaker, hypo. Kalau irregular contraction is not fibrillation, irregular. Not regular is called dyskinesia. Right? Irregular contraction is called dyskinesia. If the muscle is not contracting, say one part is contracting, the other part not, it's called akinesia. So these four terms you must know. Normal contraction, hypokinesia, dyskinesia, and akinesia. So you have to know the definition. And the best is if, well, I don't think we give you the video for echo to interpret, maybe too difficult. But we can show you, for example, like this. The piece of paper, I give it this to you. You tell me what are your findings. Of course, we erase this label lah. What is the? Then you basic anatomy of the heart, like that. You know. Right? Okay. If you use transesophageal, patient need to be sedated. You cannot do a transesophageal in a awake patient. He will bite. You have to give some sedation. The best under GA. So during CABG, patient is under GA, then we do transesophageal. We don't transferase tak boleh. So that's why during CABG we do transesophageal as a routine in our hospital. And then you know, and you can discuss with the surgeon about the cardiac status during the operation. Quickly, now, blood pressure. This is another important monitor that you have to know. Basically, you use NIBP, right? The principle of NIBP is oscillotonometry, right? Oscillotonometry or dynamic. You measure the blood pressure indirectly, and the measurement is accurate. Of course, you cannot compare with invasive technique, right? So basically, there are two cuffs. Inflating, deflating cuff, right? The one sensing cuff. When you're inflating, you're occluding the artery, brachial artery. Right? When you turn off, deflating, they're opening up the artery. So when you're inflating, occlude the artery, then it is and the sensing cuff will sense the oscillation, the movement of the arterial wall. Just before the blood flow, before before deflation. Maknanya you are measuring, you are detecting the oscillation of the arterial wall before you open up the brachial artery. So which means it is better than using using sphygmomanometer. That is, when you hear the sound, you listen. This is before the artery open up, you are detecting the oscillation from the arterial wall. So, and then you get the waveform of the blood pressure. In Japan, they use pina press. They don't use dynamic. They use pina press. They are detecting the blood pressure by putting a cuff on the finger. So they still use cuff, but they don't use oscillation, but they use infrared to detect the oscillation. Itu je beza dia kan. Tadi kalau ada map, dia ada sensor to detect oscillation directly. This one use infrared to detect the oscillation. That's why they use finger. No. More interesting is to measure the blood pressure by using invasive technique, right? So you must cannulate using ultrasound, make it routine, your routine work like possible, kan? To prevent complication, alright, to get the best result, and then you are able to interpret the waveform. Okay. Now, the reason for having a nice waveform, though, basically, is a resultant of many waveform generated by the arterial pulsation and waveform reflected back by the diaphragm, right? Maknanya blood flow, artery will generate waveform, right? Like that. Okay. Let's say this is artery lah, merah ni artery biru. This one arterial pulsation waveform. It hit the diaphragm will reflect back, it bounce back to create net waveform this way. So, which means diaphragm ni is flexible. So, it will create 1,000 waveform at any one time because heartbeat 70 beats per minute. So the resultant of the final analysis resultant of the waveform is the one you have. This one lah, your normal arterial waveform. So normal, abnormal. So normal waveform you get nice arterial waveform. Maybe I have here. This one nice waveform, right? You get a nice waveform. But let's say this is the normal nice waveform. Let's say the waveform is like this, right? Number 3, the waveform is slurred, slurred, flattened. So the system is overdamp. Overdamp means the damping factor is almost 1. Lock, bubble, thing, right? Okay. Let's say the system is a lot of spike like that. So the system is underdamped, which means DF almost 0 or maybe 0.1. So in case they ask you, this system is overdamped, the damping factor is 1. Slurred, clot, blood clot thinking, very floppy, soft tubing. The waveform is exaggerated. This is under reading, over reading. Maybe very stiff diaphragm, stiff tubing, right? The system is over reading, you get high systolic, high diastolic. You measure the blood pressure as you go down away from the heart, systolic higher, diastolic lower, right? Remember that? If I ask you to draw blood pressure taken from the radial artery, femoral, radial, if from dorsal pedis, you draw the diagram. And you give your reason why systolic is higher at the leg, in the leg, lower in the femoral, even lower in the radial. Okay. Next, I think this is the last slide about Swan-Ganz catheter monitoring. Okay. This is used to measure cardiac output. The gold standard of measuring cardiac output is by using PA catheter, right? Thermodilation technique. The anatomy you can see from here. Let's say X-ray. Yeah. So this is the 3D punya diagram, 2D diagram. The placement of catheter. This one, volumen Swan-Ganz catheter. The tip is in the PA. This is the anatomical figure lah, picture of the Swan-Ganz catheter. Situ. And then from there you can measure the waveform. The first, Swan-Ganz catheter ni is made from special Teflon, where it tends to soften and float in the blood vessel. The moment you put into the blood stream, it becomes softened and tend to float automatically, right? So it goes to the RA, you get this CVP waveform, right? So you know what is ACV, XY, So as you go to the right ventricle, you get right ventricular waveform up to 0 to 30. So 30 to almost 0, right? Systolic 30, 25, 30. Okay. and then the tip will go to the PA. So this is PA, right? You get a new waveform, CVP, RA, this is the value, right? And then PA, at that time, actually at this time, the moment you enter RV as RA, you open up the balloon, it will float, float to enter here, you get this, that it will float to follow the blood flow to the PA, you get PA pressure waveform. This is the pressure, 15, 25, 8 to 10. And then when it starts to the narrowest, smallest PA vessel, you get wedge pressure, PCW. So you cannot float the catheter for a long time, maybe 1 minute, then you deflate. If you keep deflating, because pulmonary infarct. So this is the limitation of Swan-Ganz catheter to measure cardiac output, right? To measure cardiac output, you use the thermodilation technique, right? Thermodilation technique to measure cardiac output. So this is the gold standard of using measuring cardiac output by using thermodilation technique. PA catheter thermodilation technique to measure cardiac output. Okay. Now, this is the picture. Let's say I give you this piece of equipment on the table. You should be able to identify what are these lumen for. All this you must know, right? Standard. One of you will get it. Don't worry, you'll get it for sure. And then the placement too. Okay. Now, to get decision, you should know the principle of measuring cardiac output by using PA catheter thermodilation by knowing this Stewart-Hamilton formula. This is Stewart-Hamilton formula. Forgotten, Stewart-Hamilton. Basic physiology. So you know this formula, okay, you can become lecturer.
Okay, thank you.
Tak boleh. This is the detail of thermodilation technique. Now, this is a gold standard of cardiac measurement. Pulmonary artery catheter thermodilation technique. And measurement is taken maybe 6 hourly. You cannot keep deflating the cuff, end up with pulmonary infarct. So you have to measure 6 hourly for early. So it's not helpful. You measure every 4 hours. In between, you do not know what's happening. So the best to measure is using a PICO. So PICO will measure the cardiac output beat to beat, right? The principle of PICO is like this. You put a CVP temperature tip CVP. Dia ada thermodilation temperature. Dia ada thermistor tip CVP catheter into the RA. So you have one set there. Thermistor tip CVP catheter, one as a reference. You measure one measurement, and then you put another long cannula into the femoral artery and analyze the arterial waveform, right? So the first cardiac output measurement using thermistor tip PA just for reference, only one measurement saja. The next, so this is used for reference to use for PICO, which will measure area under the arterial pulsation, area under the systolic pulsation. Wait, so this is the area of the cardiac output. So this is arterial pulsation. You measure this area under the curve is indicating the cardiac output. So this is called calculation beat to beat by contour analysis of cardiac output. So you are analyzing the area under the curve based on the Stewart-Hamilton to measure the cardiac output beat to beat. So this system is called PICO. Maybe I'll show you the. So you have one here, CVP, thermistor tip CVP satu, and then femoral artery. Also they have thermistor tip, and then you analyze the waveform ni. So analyze the waveform based on this formula. The formula actually is the Stewart-Hamilton, and then the detail of the formula, you get Asmoran Award lah, Rashdan Award. Who else? In UM, whatever award, Danaras award. You know this formula, you get Danaras award. So actually, you are analyzing the area under the curve, and based on the first measurement of CVP tadi tu, you measure this according to follow this formula, you get bit to bit kadar output measurement, which means it is important for you to know the kadar output bit to bit rather than for hourly using PA catheter. The detail, the formula, so everything is there. You go back and read. Okay. Now, the latest, basically, you know, this is the flow track. Flow track, if you want to measure the blood pressure saja, systolic, diastolic, kadar output, kadar index, what else? So you don't have to put CVP catheter. You only measure the hemodynamic. So like here, you can measure the kadar index, stroke volume, not this one. Kadar output. So kadar index, kadar output, stroke volume, you use radial artery cukup, right? But if you want to know the SVRI, SVO2, and SVO2 ni resistant CVP, then you put CVP. So basically, flow track ni like Pico lah. It measure the area under the curve, area under arterial pulsation, because you have radial artery cannulation of femoral, kan? So you still analyze the area under the curve, and they have the formula, and then they get all these are calculated measurement. Calculated tau. It's not direct measurement like the gold standard PA catheter kadar output measurement. This is calculated measurement based on the Stewart-Hamilton formula as well as this formula, right? So you get all those important parameters. If you put CVP, you are able to measure the SVO2, the resistance, SVR, PVR, SVR, plus the volumes, the lung volumes and blood volumes. This volume here, sini.
Kita measure, kita masukkan dalam ni, lepas dia calculate.
So you press, you get the volume, which means it will tell you
CP lah, kita measure, kita masuk nombor.
what to give, what not to give, what fluid to give, what drug to give. It's a guide lah. So it will come to like a one screen with 4 angles, four column. You choose. So that point is moving continuously. So you can use that as a guide. What fluid to be given? Let's say BP low, right? BP low, SVR low. For example, BP low, SVR low. Then they tell you what to give. BP low, maybe they tell you to give fluid, crystalloid, colloid. SVR low, maybe you need alpha 1 agonist, noradrenaline. This just guide you lah. So all this based on the analysis of the area under the curve. So based on the Stewart-Hamilton formula. So this is the latest technology, flow track, basically like Pico lah. But this is least invasive lah. Least invasive. Just outline, you get kadar index, kadar output, SVR, stroke volume, right? That's it. At least you know where you are. I encourage you to use this for certain cases, not everything lah. Maybe to learn it, you can use as normal patient, 1 or 2. After that, use for high risk cases. I think I stop here. Okay, thank you very much. Reaction, you can shout, you can jump, so it can be very alarming to us. No. If you open up this socket or plug, there will be 3 wires. You see 3 wires. Brown is active, live wire, brown, or red. And then blue neutral, green is earth. So you just remember these 3 color-coded wires lah. Brown, red, active, right? Blue neutral, green is earth.
Okay.
If you cut this cable, the electrical cable, you cut, you get three wires there. These are copper wires. Green earth, light brown, and neutral is blue. So they are insulated with special material to prevent current conduction in case of leak. So this male is a male. All are color coded. Basically, the cables are color coded. The pins are not color coded. The pins are made from metal. I just put the color coded to make it easier to understand. This is a male pin, 3 pin. Female, this is 2 pin. 2 pin. So there are 3 pins and 2 pin. Majority of the equipment are 3 pin plug system. Smaller equipment they use 2 pin. Just another illustration. Active, neutral, earth. There's a small fuse there. So this is the wall socket. This is socket. Socket. Now, the earth is a very big reservoir for electrical charges. So anything goes, current, electric, it goes to the earth, be neutralized there. So most of the equipment are earth. Our equipment, big equipment, except handphone. They are, beside 3 wires, they are, third wire is the earth wire. So this is to conduct the excessive leak from the device to the earth and protect the operator or person. Okay, now the 3-pin plug is the common one for any equipment, but the 2-pin plug for smaller equipment. For example, the cable to charge handphone, 2 pin, right? Radio. So without earth, this 2 pin consists of active and light, active, light, and neutral, brown and blue. So without earth. So those equipment that use 2 pin are smaller, lighter equipment. If you look at the OT wall, there will be 3 different colors of socket, white, yellow, and red. The red, okay, this is sorry, okay. This one always lari lah. So this socket, earth, life, neutral. They put yellow. I do not know why it is yellow, right? The white is standard. So this is called single standard socket 3-pin plug system. The red one is the one that I use for emergency in case of electrical failure, right? Electrical failure, major electrical failure in the hospital. This one is still operating because the backup is from the electrical generator, right? So let's say the main power is cut off, failure, all the white plug socket are not functioning, but the red one will be functioning because the electrical supply is mainly from the generator, right? Petroleum generator. They use petrol to generate the machine and electricity. So they are color coded red. So we don't normally use this to use our equipment. We don't plug in our machine to this. This is for certain equipment, for example, halang machine, which cannot be failed at any time. Halang machine, or maybe ventilator, possible. So in case of a power failure in the hospital and your equipment is plugged to this red socket, your equipment is running. So halang machine, we use this. Hemodialysis, we use this. ECMO, we use this. Right? We cannot accept hemodialysis machine to stop because of electrical failure. So as for halang machine, right? Okay, or hemodialysis. So this is the cluster of socket. The cluster of socket, I took it from hospital UKM recovery room. They are nicely arranged. Kan? This is just for cosmetic reason, I think. Look nice. It is below the common gas outlet. That one, common gas outlet. It depends on the design of the hospital construction. This is another one, horizontal layout. Just now cluster. This is along the pendant. So up to you where you want to have that type of design. Now, the current we're having now are AC, alternating current. Which means the current is electron, it move forward backwards. So this one AC current, the current flows to and fro, backwards, forward, at certain frequency. So we use just now 50 hertz, which means 50 times per second. Like that, 50 times, 50 to and fro, 50 times per second. So this means 50 hertz. Right? Okay. Now, DC current is mainly come from battery. Your dry battery, the everyday battery, national battery, all this battery. Like here, the battery here is DC, DC current. Okay. Most of the hospital we are using AC. Houses, hospital, and other premises, AC. DC is used for your remote control, for example. Remote control and maybe minor equipment, small equipment. AC is more harmful, more dangerous. You touch AC current, you may die. You may get electrical shock and die. DC you can swallow, no issue. You swallow the battery, end up with gastric perforation.
Bijak sikit lah, bijak sikit. Okay lah. You can swallow battery is DC, so that's harmful. Okay, fine.
Aduh.
Okay.
100 million more dangerous.
Now, whether the current is dangerous or not is depending on the voltage, the ampere or milliamp, as well as the frequency. Frequency will determine, for example, like surgical diatomy, which has up to 1 million hertz, which is not harmful to the person. It only calculate, but it doesn't cause electrical shock, which means the frequency of the current move forward backward will also determine the hazard or complication of the electricity. Okay, what about current density? Current density is also important because it may determine whether the area is burned or not burned, which means if one small area you pass through very high density of current, will focus there, it can cause burn. For example, diatomy plate, surgical diatomy plate, if you don't put in contact properly with the skin, it can cause burn because the current density will be focused in one small area, it can cause burn. That's why when you put diatomy plate, you have to put it properly, which means the whole plate should be covered, placed onto the skin nicely without area which are not in contact with skin. Okay. Number 3, the wet skin is more vulnerable to electrocution, which means wet skin has a lower resistance, we allow more current to go through. So that's why when we're in the OT, we prefer to have dry hands or wearing glove, right? Because dry hand, you're wearing glove, that will increase the resistance to current. So current will not flow easily when your hands are dry or you're wearing glove. So when you're doing procedure, beside cleanliness issue, you prevent current electrical hazard. That's why you use glove. Or if you want to touch any cable, you must touch with your dry hand, not wet hand. Now, if you remember your physics and electrical law, this is Ohm's law, whereby the current is dependent on the voltage and resistance, right? So I equal to V over R, or V equal to IR. So, as I mentioned here, the voltage is 240. In Malaysia, the voltage we use 240, fixed 240. Right? In US, I think 200. Australia 240, UK 200, 240. Standard international voltage is 240 volt. If you look at this formula, I is current. A current is determined by the voltage over resistance. That V is constant. So the important parameter is the resistance. So basically, resistance will determine the current that flow through the body. Remember the formula? A very simple mathematics, right? V is constant, so the I is dependent on the R, just like your flow. Flow equal to blood pressure over resistance, right? So resistance will determine the current, and so the flow. If resistance 0, your flow equal to the pressure. So when you are checking the blood pressure in the OT, you are actually checking the cardiac output, assuming R is constant. That, just like that. So here, V is constant, 240 volt. R varies. If you have higher resistance, current is low. That's why right hand has high resistance, the current is low. Right hand has low resistance, so the current will be high. You just follow the formula. Okay. Now, this is the typical electrical flow in any equipment. Okay. Let's say this the power supply. This is from socket lah, wall socket ni. Socket. So power supply standard 240, frequency 50. Active, neutral, you have a toaster there. So you turn on the switch, the current will flow through this supply to the active wire cable. It goes to the toaster, the bread get toasted, get cooked, and then the current will go through the same amount of current, will go to the toaster, back to through the neutral, and back to the supply. So let's say I put in terms of number, 10 electron going through here, go to toaster, back to through neutral, back to the supply. So 10 coming in, 10 coming out. There's no leak in between active and neutral. Understand? Which means 10 going in, 10 going out. So the same amount of current in the live and same amount of current return through the neutral. Alright, so there's no leak. Alright, the amount of current going in, amount of current going out is the same. So it is a safe machine. You can use this machine. Okay. Let's say for a person who is touching the live wire, current here, live current, I'm touching the live wire, I may get electrocuted because the current will go through my body back to neutral, right? So my body may get burned depending on the resistance in my hand. Right? Let's say my hand is dry, resistance is very high. So I'm okay, the current go through my body, I'm okay because my resistance is high, it returns through the neutral back to here. Okay. Understand, Okay. For example, let's say the machine is faulty. Your ECG machine is faulty, your IBP machine faulty, even your J machine display monitor is faulty. So, and I'm handling the monitor, right? Okay. The current going through live wire, active wire, go through the faulty machine. Let's say this is Dynamap or ECG or your monitor, faulty. It's not properly serviced. There's a leak there. So going in 10, for example, 10 through my body, goes back 8 to leak. And this leak go through the earth. Understand? Maknanya, going in 10, going back 8. The different 2 will go through the earth and back to the supply. So total 10 here, going back 8 through neutral, 2 through earth, back to the supply, still 10. But there's a 2 current of 2 is leaking through the earth, right? Understand? So this 2 ni can cause electrocution. If your hands are wet or wet. So this is what we don't want. So how do you know that the machine is faulty or not faulty? You have to check it regularly. So this is the job of the electrical technician or bioengineer. Yeah, very dangerous. Okay, I give you the example in terms of calculation. Okay, this is the calculation. It's very simple. Let's say the current from active supply to through active wire go through you. You touching it, or you touching the machine, and your hands are wet. And when the hands are wet, the resistance is very low, right? So the current will go through the lowest resistance, which is through your body, because your hands are wet. So this current will go through here. Maybe all the 10 will go through your body because your hands are wet. So you may get electrocuted because your hands are wet. Over here resistance is high, over here resistance is very low. So how much current can pass through or go through your body? Very simple. Say the voltage given fixed 240, the current, so the resistance in your hand is very low, 1000 ohms. So you divide 240 amp divide 1000 ohm, 0.24 amp, which is 240 milliamp, and this can cause VF. You see the danger of having wet hands touching a faulty machine. That sometimes when you're touching the TV antenna, you get a bit of tingling. There's a current leak into the antenna, which is normal in any TV. In Japan TV, it's normal. It's small current leak. Even you touch with dry hand, it's normal. It's bit sensation, it's normal. But if the leak is huge, and you are touching the equipment with wet hand, this can happen to you. This is fake 240 amp. You have wet hands, low resistance. The amount of current that go through your body, not to return through neutral, but through your body, because your body has a very low resistance. This is the amount of current that passing through to your body, 240, and this is good enough to cause VF. So you go like that. You don't need. So be careful. That's why you make sure your hands are dry. When you handle the machine, make sure your hands are dry. Okay, let's say your hands are dry. Machine is faulty, the same machine is faulty. Ada leak kan? Maybe the wire is not properly connected, ada break kan? All wire, eaten by a rat ke whatever. Okay, so the same current going through your body, but your hands are dry, resistance is very high, 800. So 240 divided by 800, 0.003 amp, 300 microamp. You touch it, just a bit of tingling sensation. You survive. So handling equipment with dry hands is important. So never ever touch equipment with wet hand. Never ever in the OT. At home also. Let's say you are having your shower, hot shower in the bathroom. Before you touch the button, make sure your hands are dry. Then you have a shower. Not to have shower, then press the button. Make sure your hands are dry, then press the button or hot shower. After that, don't touch. Because if there's a leak there, you will be electrocuted. Understand? There were cases, right? So once a while, you must check your hot shower lah. There's a small button at the bottom. It's called ELCB. I'll show you later. you by pressing that, you are testing whether the machine is faulty or not faulty. That's why, as I said there, when you buy an equipment, you must check the instruction. That's important. Even for small handphone, you must read the instruction. Okay. Okay. This is the numbers or values that you must memorize lah. This has come up many times in the MCQ or BAQ about the amount of current that can cause hazard to human body. As I said, direct current flowing through your skin, 300 microamp, you got tingling sensation. It's nothing lah, tingling, you know, tingling, right? 500 microamp, slight pain, pain. 1 milliamp, 1000 amp, pain sensation. 3 milliamp, muscle contraction. Say 10 to 16, you cannot let go. This can happen, for example, during the flight, the lampu jatuh, the person is being electrocuted. Then you want to help him. You touch his body, you get electrocuted as well. Because you cannot let go. Let's say that person is struggling from the cable, and the current that flowing through his body is 10 milliamp. You want to help him. Your generous heart, okay, I will help you. You touch him. You get stuck and you cannot let go. And you die lah with him. That's why when you want to help a person who is being electrocuted, you must use something that has high resistance. Wood, high resistance. Not metal. Metal is a good conductance. Body, good conductance because we have electrolytes. We have current in our body. So you take a wood, then ask him to hold the wood and you pull him out. Don't use your hand. Okay. 20 milliamp respiratory paralysis. 100 to 200. This is direct contact. VF. As earlier on, the faulty machine, if the current is 100, you get VF. Be unconscious with VF. If you're playing football during raining seasons, thunderstorm, the current is very high. You get struck by the lightning, you're dead. Shock. This one. This is the current is very high. That's why when it's raining, thunderstorm, don't play football, don't play futsal. Futsal is indoor, kan? Football, or rugby, because you're struck by the lightning. That's it. Because the current is very high, up to 10 amp. No. So this is a simple diagram to show the current flow in the OT, for example. Power supply from your socket, left. That this is in the socket, this socket lah, socket ni. Right, socket. Socket there. Live, neutral, earth. Just remember these three. Live, active, neutral, earth. So the current goes this way. This is socket, Ini socket, ini socket. Ini terbalik. Sorry. From here, your equipment there. This is plug, ini plug, right? Ini plug, socket, right? So the supply this way, right? Return. So say 10, went back 10. You get functioning equipment lah. This is behind the wall lah. This one, this part is behind the wall lah. Behind the wall there are cables lah to the main supply. So you plug in your ECG, right? So the current come this way like this. You get functioning ECG machine, right? So inside this plug, inside the plug and socket, this is a plug with 3 points, socket with 3 female, plug with 3 male. Inside here, there's a 13 amp fuse. Inside here, inside this plug, ada 13 amp fuse, small fuse, right? Very small fuse. Is a protector. If the current is more than 13, it will blow off. It blow off. Let's say the current that going through here is more than 13 amp, it will blow off. Disconnect the supply lah. So So normally the current that going through here is less than 13 M lah. 13 M is very powerful. So unless there's a current surge, for example, during thunderstorm, sometimes there is a current surge, kan? Then the current that going through here may be more than 13. It blow off the socket, socket and the socket. Okay. Now, in your house, I normally maintain my electrical circuit on my own. I do it on my own. I fix the fan, hot shower, light, ni semua I do it on myself.
Excellent.
But I don't have certificate for doing that. But I know when I learn from my friends, electrician, how to fix all these electrical appliances, wires, lampu, light. So inside the house, there's a small panel. The panel, there are few fuse, panel fuse, and inside there's a circuit breaker. Circuit breaker. So basically, circuit breaker is a protection from you to get electrocuted. Circuit breaker is a device that prevent excessive current that can go through the machine. It is like a fuse, but it disconnects the supply. If let's say the maximum supply is 20, but the current going through the machine is 25, it will cut off. That is the function, circuit breaker. It protects excessive current that can go through the house, for example. So the amount of current will be set by the contractor. Okay. So let's say the equipment is faulty. Let's say your hot shower is faulty, or rice cooker is faulty. The current go through active, right, to your rice cooker. Rice cooker is faulty, so some of the current will be leaked through the earth. Some will return to the to neutral. So to the earth either this way or this way, doesn't matter. So let's say, as I said earlier, let's say the amount current going through here 10, faulty machine, 2 going through here or here, the end return through here. So if you touch this machine, you get the effect. The amount depending on your hand, dry or wet. Now, let's go back to the practical scenario. This is the one I took it from the OT. I think the same OT everywhere. OT, this is a clock. Okay. If you look carefully, temperature is indicated there. 18 degrees Celsius. Is it 18? 18.3. Humidity. What is this? 36, 39. 36. It's very out. 36. So this I think this is 2 set of humidity and temperature measurement. So 18, 17. I think the 2 set just to compare. Humidity 39, 36. Okay. Ideally, for the main OT, ordinary OT, temperature 18, 20, adult OT. Humidity 50 to 55. This is very dry, 36. So it's not good for your skin. You get cracked lips. Being here for one day, you got cracked lips, dry skin, so not good for the ladies. So you make sure your OT is 50, 55. I know you never check this, you never bother, right? About temperature and humidity, but it's important for you to know. Because let's say the humidity is 80, I won't start the case. I won't. Because it will cause infection. It will facilitate, or it will cause infection because the area is very wet, humid. That's the reason why you need optimum humidity 50, 55. 80 is very humid, you get infection. Right? You get SARS in the OT or Wuhan. So that's why make sure before start. I think last month, when was in UKM? No, in UITM. humidity was 85, I stopped the list until they rectify the reason why the humidity was very high. So it's not suitable for operation because it will invite infection. So you must, this is too dry, it's good. You don't get infection, but it's too dry. Then you need a lot of IV fluid, fluid to the patient, to you as well. You feel thirsty because it's very dry, you drink a lot. So it's not ideal. So this is what you see in the OT. Humidity, temperature, and then what else I show you? This one, the gases supply, right? Gases supply. Maybe I have another one after this. It's not there. I want to show you the other LIOM name. Never mind. I just continue. I will go back to that. Now, in the OT, they actually you classify equipment into three lah, basically, kan? The class 1, satu class 1. Class 1 is divided into two. Class 1 CF, where the amount of current allowed to go through the body is very minimum, 10 microamp. This is the area where you are doing intracardiac procedure. For example, inserting CVP line, pacemaker, cardiac catheterization, or CABG, any procedure where you are in contact directly with the heart. So this procedure must be done in OT with class 1 CF, where the maximum current that can pass through the body is 10 microamp. So this is standard. Example, in CV lab, CABG OT, or any area where you are going to perform CVP insertion, pacemaker, angiogram, or all those things that related directly to the heart. So this is the area where you should use. Area with electrical supply belong to class 1 CF. The current allowed is 10 microamp. The symbol is this, symbol heart. So if you look at the monitor, they put this label, monitor equipment. At the back, you can see this label, which means this machine is belong to class 1. Class 1 CF, class 1. No. The other one, class 1, but is BF. Ini CF, ini BF, 1 juga. But the current is slightly higher, 100 microamp, right? 100 microamp. Both current, 10 microamp, 100 microamp can cause VF if it get contact directly to the heart. So this is just a classification, but you don't worry very much. But if you know, all cardiac procedure must be done in class 1. That's it. It's more than enough. Any cardiac procedure related to any cardiac procedure, you must do it in dedicated OT where the electrical supply is belong to class 1. The class 1 is further divided into two. This is the ideal, cardiac CAT, civil lab, CABG, pacemaker. This is the place, 1 CF. The other one, 1 BF, slightly higher than 1 CF, because the setting of this electrical classification is different. The 1 CF is more costly. Itu aja beza dia, kan? And safer lah for cardiac procedures. This is less safer. You can, but less safer lah. You can still do it. But don't do cardiac procedure in class 1B. Earlier on, they class 1 CF, 1 BF, 1 class 1B. So class 1B is mainly for a bigger machine. Let's say hemodialysis machine. So there are areas for hemodialysis unit. It's not simply convert what into hemodialysis unit. Cannot. You don't do that. Cannot. There must be a specification whereby you can place your machine here and there. So you're not simply, I want to use machine using this socket. That's what, no, not like that. There must be a dedicated area for hemodialysis machine whereby the current leakage cannot be more than 500. So like that. Now, again, for heavy equipment, let's say X-ray, you cannot simply use X-ray cable, plug in here, you can't. Tak boleh, because the current is so small. It's not meant for X-ray, not meant for CT scan, for example, because they need more current, higher current. So, for those equipment which require higher current, this is the symbol. So you have to provide double insulated, double layers of insulation. So when you touch it, you are protected, yeah? Because let's say the cable for X-ray, a big cable, right? Very big, not like ordinary cable, big cable. You step it, you hold it, you're okay because the insulation are double. If they use one insulation, you get burned, you get electrocuted because the current is very high. So they use double layers of insulation to protect the operator, the radiographer, for example. Right? This is the symbol. Okay. The battery is straightforward. Okay. Now, as I mentioned earlier, microshock occurs when the current going through your body via the skin, right? So you need a bigger current to cause VF up to 100 milliamp, which means it's not easy to get electrocuted by touching all those faulty equipment, unless your hands are wet. If your hands are wet, then you may get electrocuted. Just remember in your mind, whenever you want to touch an equipment, your hands must be dry, or you wear gloves, right? We do not know whether this machine is faulty or not. We do not know. We assume the machine are okay, but we never know, okay? We never know. So as I said, 100 milliamp, 100 milliamp, you touch, it can cause tingling again, Sorry, 100 milliamp, this one 100 milliamp. This is 100 microamp, milliamp, 100 milliamp, there, VF, right? So, you don't get this amount of current to pass through your body, very unlikely unless your hands are wet. Itu saja. If your hands are dry, you are safe because the current I showed you earlier is very minimum. Right? Again, I want to show you again. If the hands are wet, this is the amount of current that passing through your body, 240, you get VF, right? So this is called microshock, because there is no direct contact to the heart. So you can get VF if the current is big enough passing through your body. That is about 100 milliamp. This is more than 100 milliamp. You get electrocution, and this type of electrocution is called microshock. Okay. Now, all right. Let's say you are ironing to make your baju beautiful, more elegant, and your iron is faulty, right? And the amount current that passing through your body 240, you can get electrocution. You can get VF on the spot because the current used by iron is very high, very high. So the machine iron is faulty, and the amount current leakage through the machine you're holding is 240 and above, you get VF straight away. So that's why when you are doing ironing, make sure the cables are intact. That black white strap, white strip, right? You must be intact. The cable should be intact. The microshock is different. It occurs when there's a direct contact to the heart. For example, the catheter, your CVP catheter, what else? Your pacemaker catheter, or when you are operating directly onto the heart, CABG, which means there's a direct contact with the heart, and there's a faulty machine, the current passing through the saline catheter, right? Or passing through the pacemaker cable, or passing through the to the knife or scalpel or artery, which is in contact with the myocardium, you get microshock. In other words, it's a direct contact. You have a current directly in contact with the heart. So this is microshock, which means the current required is very, very low. So it can happen. Let's say your CVP line is in the RA, right? The machine is faulty. The current will travel from the faulty machine to the saline field catheter. Saline is a good conductance. So if the current is 60 microamp passing through, going through from the machine, faulty machine, to CVP line, to the right atrium, he will end up with VF. That's why you have to be careful when you are doing cardiac procedure. You must do it in the class A,
Plus 1.
1CF. This is important, all right? So, but in our normal practice, we seldom see this because we assume machine okay, most time okay lah. We never know kan. Once a while, because of our unfortunate day, very unlucky, we end up with this unexpected detrimental event. Okay, example like this. The machine is faulty lah. The current leak is very little, say 100 microamp, but you are handling the heart. You are putting a CVP into the heart. So the small current, 100, for example, 100 microamp passing through the heart end up with VF. So example here, okay. Say the voltage 240 fixed, and then the resistance is very high, but there's a direct contact to the heart via the saline catheter or pacemaker cable, kan? Even though the resistance is high, but the amount of current to cause VF directly is very small, 300. So this is direct contact with the heart, you end up VF. If you touch with your hand, there's no direct contact with the heart, it's okay. Doesn't matter, just tingling. But this amount of current is in contact directly with the heart, you get VF. That's why CVP catheter, pacemaker cable, cardiac catheterization, right? CABG, they must be done in dedicated OT or area, and they have to make sure the equipment are perfect. That's why they check all these halal machine before they start. They check the all CV lab machine before they start. Pacemaker, they check everything because the small current can cause VF, unnecessary VF. So, okay. Now, how do you prevent all this hazard from occurring? Basically, there are three mechanisms to prevent this from occurring. Number one, I mentioned earlier, circuit breaker, like a fuse, a circuit breaker. Number two, ELCB, earth leakage covalence. Number three, LIM, or LIOM, LIOM or LIM. Let's one by one. This is the typical 1980s electrical supply, power supply to the house. Okay, 240 voltage, 240. Every return. The modern one is better lah, look beautiful, all electronic. So the Hertz 50, right? All right, 1974, manufacture date, right? This is rotating this to show the amount of current going through the house, rotating. So the voltage, the frequency, the current range 10 to 50, ownership LLN. This is the old monitor lah, old power supply monitor. This is the counting meter to indicate the amount of current you have used. Okay. Inside the switch box, the meter is outside. Next to the meter switch box, there are fuses, at different rate. This is the amount current that it allows 32, 20, 32, 10. So these are the fuse to indicate the current load. For example, over here one cable. So 1, 2, 3, 4, 6 cable example. This cable can stand up to 32 M. 32 M. You need 20. Let's say the current going through here is 50. This will get disconnected. Because maximum current that can go through this fuse is 32. Now the current flow is 40, for example, you get disconnected. Trip, tuk, like that. Understand? So blackout lah. Blackout to the socket supplied by this fuse lah. That's why at home there are many fuse to different areas. One room maybe one fuse, one supply. Living room maybe you need a bigger 32. Kitchen maybe 20. Your bedroom maybe 10, right? Because in the living room you have a lot of things there, so you need more current. So let's say the current load maximum 32 amp. Suddenly a current surge of 40, which means this fuse will get disconnected for that particular area, living room saja lah. So this fuse actually they are actually the circuit breaker to protect the user from getting excessive current. Remember, understand? Okay. Over here, I show you. This is the main on and off. This is the circuit breaker, like basically. This circuit breaker. This is you push the knob up is on. This is on. So the current load 63 amp, right? So if the current load, the current surge more than 63 amp, it will get disconnected. So the maximum current that this machine, this monitor or fuse can accommodate is 63 amp maximum, right? Which means 63, for example, 63 going in, 63 going out. Or let's say 20 going in, 20 going out, it's okay, right? 70 in, disconnected, okay. Let's say going in 60, going out 58, trip, because the trip there 100 milliamp, which means there's current different. Understand? Going in 60, going out 58. The 2 amp different will cause trip, which means disconnected. So that's another feature of safety feature, which means the current going in should be equal to the current going out. If there's a difference, it get disconnected. Okay? Okay. This is an example of circuit breaker. Okay, now the circuit breaker, CB or fuse. Number 2, the ELCB. The second method of preventing electrical hazard is by using ELCB. Earth leakage core balance is normally used in non-cardiac OT. Now modern OTs they use all class 1. All OTs regardless cardiac, non-cardiac, all class 1. But older OT, they use ELCB, or at home, especially certain devices like hot shower, iron, electrical cooker, or those appliances, they use ELCB to protect the user. It works like this. Very simple. I make it simple for you, don't worry. Okay. This is the hot shower using ELCB. This is Panasonic. So, over here, there's a knob at the bottom there. ELCB test, right? You on the machine, your red light there, red or green light on. So you press this button to test, which means the machine is okay. If you press, it doesn't sound the machine is not okay. Dangerous. You must test before you not to every time you test lah. I mean, once a while you test. Before you on, make sure your hands are dry lah. Then you on lah. Don't use wet hand to on and off. It's not safe lah, because we do not know whether this machine is faulty or not. Unless you test it regularly, once a week, once a month you test. Okay. So what happened in ELCB? Ideally, I said the current going in, say 10, going back must be 10. So there is no difference between live and neutral, kan? Masuk 10, keluar 10. There's no difference. If there's a difference between live and neutral, then it's not normal. right? It's not normal. Okay, it's not normal. I show you. Okay. Okay. Let's say the current going in 10. The current return 9. So difference of 1 milliamp kan. So that will disconnect the system automatically because the LCB it uses very little current difference though. The current difference more than 10 milliamp, very little, it will disconnect the system. As little as 10 milliamp difference between live and neutral, it will disconnect the system. Understand? Maknanya, let's say the oncoming current say 10, the return 9, the difference 1 amp. There is a big difference. It will detect as little as 10 milliamp. It will disconnect the system. That is to protect the user. So this is used in many appliances, including that hot shower. So it's good. Okay. Number 2, the fire's warranty some more. Okay. So the current going through the live wire to the electrical equipment, the amount should be equal. Which means the current in the live wire must be the same as the current in the neutral. So the amount of current going through L is equal to the amount of current returned through N. So there's no difference, which means the machine is safe, you are safe, right? Okay. Okay. Let's say the same system, the current going in, current going out, but the machine is faulty, right? So going in 10, going out 9.8, for example. The difference is 0.2 amp. So this system will be disconnected automatically. Okay, because 0.2 amp is big. Earlier on I mentioned it detects as little as 10 milliamp. Right? 1 amp is 1000 milliamp. Right? So this is a good mechanism to protect the user. Now in the OT, we don't use circuit breaker or ERCB to protect the patient. So we use those two plus LIM. Maknanya we combine these three method. But mainly in the OT, circuit breaker is the top priority there, the main, and then below it is LIM or LIOM. I show you the diagram. Basically, this is your Hala machine, for example. This is the power supply. There's a isolation transformer which separate these two systems, right? There's no direct connection between supply and equipment, and these two are separated by a transformer called isolation transformer. So which means this circuit is 100% independent, right, from the supply. That's why they call it isolation transformer or line isolation system, LIS, or line isolation monitor. The same name like LIS, LIM, LIOM, the same. So how does it work? As I said, this circuit is isolated from the main supply, so you can touch lah. You touch is okay, no problem. You can touch a live wire, you are still alive. You touch the neutral wire, you're still alive. Okay, even though the machine is faulty. So, machine is faulty, it's okay because there's no direct connection between this electrical system and the supply. It's what I call isolation transformer. Right? But you cannot touch with both cable. You cannot touch live and neutral with two hands. So you complete the circuit. You get electrocuted. So I think it'd be ridiculous to hold all wires together, kan? You one by one lah.
One by
Kan, you cannot hold 3 wires with one hand, cannot. You have to do one by, because the electrician when they do repair, they do one by one using the magic pen, the
Magic wand.
okay. Now the LIM, this is the one I want to show you. This is the OT, this is LIM. Can you see this? Wait, let me put it. Okay, this one old one, okay. This is the LIM, LIOM, or LIS, the same. Over here, there is an indicator to show the current that is flowing to the OT, the current, up to maximum 5 M. I show you in the electronic device later. So if the current use is more than 5 M, it will give an alarm. Maknanya you are overusing, you are using more than 5 M at any time. So this one will blink lah, alarm bunyi. This is the old one. The modern one is, it looks like this. I think you see this in the OT, kan? Okay, so this is the current, maximum current here, 3 M. They put 3 aja, 3, not 5. 3, the old one 3, 5. So this is the amount current milliamp that going through the machine you are using. All machine total only 1.8, tak banyak, kan? Maybe this is not cardiac lah. So if the current is more than 3, it will give an alarm, indicating you are using more than you expected. You are using more than 3 M, so be careful. Maybe you have to reduce, or you have to stop, or you use one by one lah. This is non-cardiac, cardiac more. So this is just a warning. It doesn't prevent electrocution. Just a warning. They're using more than you're supposed to use. You are supposed to use, let's say, 2, not more than 3 at any time. So this will tell you about the LIM, just an indicator that you shouldn't use more than this in that OT, right? Remember, because the current we're using, they are arranged in parallel, though, not in series, kan? In parallel. So you have 1, 1, 1, 1, total 1. Let's say you have 10 equipment, all in parallel. So one equipment use 1 amps. So 1, 1, 1, 10 still 1, because they are arranged in parallel, not in series. It's again same, 1.6. Okay. I think I stop there. I think I haven't finished. Now, I will give you the list of method how to prevent, or tips how to prevent electrocution later. Surgical diatomy, it won't cause electrocution or electrical hazard, because the voltage is 240, but the frequency is not 50. The frequency is up to 3 million hertz. As I said, if the current flow is very fast, up to 3 million hertz, it won't cause any harmful effect to the person. If you use 240, 50, you touch, you go, right? You touch it like fire. But if you use 240, frequency 3 million hertz, you touch, you smell, which means the amount of current that go through your body to cause harm is dependent on voltage, number 1, number 2, the frequency. Okay. So the principle of diatomy, there are 2, unipolar, bipolar. Unipolar is for cutting, for coagulation, because unipolar uses higher frequency than bipolar. Okay. So unipolar is meant for cutting, coagulation, both. The diagram is like this. Okay. Diatomy machine, high frequency current, 3 million hertz per second. This is the probe or electrode for cutting or coagulation. So there's high density current at the tip of the probe. You cut, you can cut, you calculate, the amount current will return to the diatomy plate. So this way, which means the circuit is complete. Machine, probe, skin, cut, coagulation. This is diatomy plate. You put it in the tire, for example, to disperse the current. and back to the neutral, back to normal. So this is called unipolar, whereby the circuit is complete. It goes from the machine to the probe, to the body, diathermy plate, back to the machine. It's a complete circuit. So this is called unipolar, meant for cutting coagulation. The important aspect here is here. This is important. Let's say your diathermy plate or this specific plate you place in the tie is not in good contact, it can cause burn. Because the role function of this is to disperse the current. Disperse current to become less density current. It doesn't cause burn, and the current will return through here back to the supplier, power supply. So unipolar is meant for cutting and coagulation. For bipolar is only meant for coagulation. Bipolar, okay. Same, the current supply, high frequency current, 2,000 million, 3 million. This is the probe, right? The probe. And the current doesn't go through the body, through the plate, back to the power supply. It only goes from the supply, tip of the probe, then return through the neutral. So on this way. So the circuit is not complete because it doesn't go through the body fluid to the diathermy plate. So there's a difference between unipolar and bipolar. So in terms of frequency, I think this one need more higher frequency. So I just refresh. For cutting, you need less frequency, 1 or 2 million hertz. For coagulation, you need higher frequency up to 3 million. And the current does not pass through the body fluid to the diathermy plate back to the neutral wire or cable. Therefore, this bipolar is only meant for coagulation. So it's not strong enough to cut the tissue, skin or bone. So, which means surgery like neurosurgery, eye surgery, anything that you need, you don't have to cut, you can use bipolar. Right? Understand? So it's not as good as unipolar. Unipolar you can cut, you can coagulate. This one you can only use for coagulation because the current doesn't go through the body fluid and return to the machine, to the power. So, right? Okay. Now, what about surgical diathermy and pacemaker? So, now when the patient is having pacemaker, never ever use unipolar. Okay? Do I have the note here? Yeah. No. Okay. So never ever use unipolar diathermy when the patient is having any type of pacemaker. Doesn't matter, demand or fixed, right? If possible, try to avoid unipolar. You must use bipolar, which means if you use unipolar, the current will go through the body, through the heart, body back to the diathermy plate, right? So the pacemaker can get wrong information, wrong signal, additional signal, which come from the diathermy. So the pacemaker get two signals, one from the pacemaker side, one from the diathermy. So it may get confused. It may not function. So unipolar diathermy can affect the function of the pacemaker because the pacemaker may receive additional signal from the diathermy that it will interpret differently. That's why if you need to use unipolar in this type of patient having pacemaker, you must have a magnet, which means you convert the demand pacemaker into fixed. You fix the rate 70, for example. Whatever happen to the patient, the firing rate is still 70, which means you need a magnet. So you put a magnet over the pacemaker, convert the demand pacemaker. Nowadays all demand fixed, very rare. You convert the demand into fixed pacemaker, you set lah 70 ke 30, 70 ke 60. So the pacemaker will fire 70 beats per minute regardless you use unipolar ke bipolar, doesn't matter. The magnet is special magnet lah, special magnet. ordinary magnet, but it's designed for pacemaker. Put on the pacemaker lah. Then you get fixed rate. You can see the pacemaker tracing. Let's set 70 to 70 lah. 70. Regardless, you use unipolar, which means you can still use unipolar diatemy provided you put the magnet on the pacemaker. That number one. Let's say you don't trust this, or you're not very confident, you don't feel confident. What you can do, pacemaker is here, right? Like a surgery in the leg, right? So you put the diatemy in the leg here, surgery here, so the current won't go through the heart. So it is okay. Let's say you're operating on the knee, TKR for example. Pacemaker there, TKR here, put diatemy here, so you can use unipolar because the current will travel around here saja. Understand? Right? Or here it's okay. Let's say surgery in the right shoulder. You put diatemy where? A plate here. The current will flow this way or this way also. So a bit dangerous like kan. Let's say surgery is here. Pacemaker here. Even worse. Right? Pacemaker here. Surgery, whatever you cross, like surgery left leg, pacemaker here, and then the current will go through the heart. So surgery here, surgery here, heart pacemaker here, diatemy here. So it will complete the circuit. Tak boleh. Even here, you put diatemy plate here, still crossing the heart. You put diatemy plate here, even worse. Understand? Even worse. So if possible, in that case, you use a magnet. Let's say surgery left leg. Surgery right shoulder, diatemy left leg, right leg. Okay, still you need a magnet. Surgery left shoulder, diatemy plate, left leg is worse, right? Because it goes through here. So the best thing is, if you want to cut the tissue of bone, use a magnet. But for certain surgery like eye surgery, neuro, you don't need cutting diatemy. Can use coagulation. Okay. So before you decide to use unipolar bipolar, first thing to do is to contact with the pacemaker dealer. Make sure the pacemaker is, there are few conditions before you subject to diatemy. The status of the pacemaker lah. In fact, you can talk to them to convert by electronic means. Nowadays, you can convert electronically, because they use all this Wi-Fi, all those things. They can convert from demand to fixed, and then to keep it fixed, you have magnet standby. Okay, now these are the precautions for surgical diatemy. Number one, if possible, use bipolar for those with pacemaker. If you have to use unipolar, you have to use it in short bursts. Ataupun you use magnet. Okay. Which means you are converting the demand to fixed rate pacemaker. Okay. Now, finally, with all this, your ultimate aim is to prevent electrocution, right? To the operators, including the anesthetist or the surgeon or the MBS. Number one, all electrical equipment in the OT ICU you must inspect regularly, which means this is the job of biomedical engineer. So they have a regular timetable. They will inspect, examine, check all this equipment, say every 6 weeks. So that's the job. They have a small logbook to check the GE machine in terms of electrical function. Number two, you use electrical equipment that conform the electrical safety classification. So let's say you want in cardiac OT, you must use devices that conform to class 1 CF, for example, because you're dealing with the heart directly. So any procedure related to the heart, you must use equipment belong to that class 1 CF, for example, to minimize the risk of electrocution. Number 3, procedure must be done in appropriate designated area. Yes. Number 3, all equipment must be which means try not to use 2-pin socket lah, 2-pin plug. You must use 3-pin plug where the third pin is earth. So all EE must be earth. The green cable wire from the machine to the earth. You must use good insulation for wires and casing. For example, this one is not, let's say it's a break in the insulator, don't apply tape. So you dispose, get a new cable, for example. Because this insulator provide high resistance to your wet skin. Even if my hands are wet, I'm touching this. In case of faulty machine, I'm okay because this insulator is very thick and has high resistance. So that's why all machine should be well insulated as well as the cable. Nowadays, the GM machine monitor ni, the casing is not metal, neither stainless steel. The casing is epoxy, which is non-conductance. So they don't allow current to go through that casing because casing plastic okay, epoxy okay, not metal. Metal are good conductance. So and more expensive. That's why all the equipment, all plastic, epoxy plastic. Because one of the reason they are cheaper and they are non-conductance to electricity. That to protect the user. Okay, the next one. Okay, you use those measures, circuit breaker, ELCB or limb. So in the exam, they don't ask you the detail of this device, how does it work. They only ask you MCQ or BAQ. The method of preventing electrocution include circuit breaker, true, limb, true, ELCB, true, tan, wrong, something like that. They're joking like limb is LIOM or this. And then do not place IV fluid on the top of any electrical equipment, which means don't put your drink IV fluid on the equipment. Never ever put your IV fluids on the equipment. We never know if there's a leak, water leak, saline leak that can conduct electricity in a faulty machine. Do not handle equipment with wet hands. This is important. Use dry hand, not hand. Do not cover your machine ventilation holes. So do not cover to make it beautiful. Don't cover the body of the or casing of the equipment. Never ever. Even your TV, don't cover the rear ventilation hole. Don't leave it open for air to move in and out freely. Do not push trolley extra machine over the cable. That can damage the cable. Do not use extension cable or plug. Never ever. But we are doing it every day. We shouldn't do that. I think it's our culture to use extension cable simply because we have a wrong design for OT. That's why you have a good design for your OT. You don't need cables. So you have to work out how many socket you want in that pendant. You have to work out before when you are constructing the OT to avoid using extension cable, right? So the electrical point should be on the pendant, not on the wall. Try to avoid the wall socket. Must be pendant, small. So everything comes from the top to down. Because there's a cable like this, I can simply step on it, all right? I can fall because of the cable, so it's not good. So do not use essence cable. It's very dangerous. There were cases, operator get electrocuted because of exposed wire in the damaged extension cable. They are lying on the floor. So this is one example, a bad example. Having one single, actually only one main socket now. The main socket is here. This is a main socket. The main socket here.
They break the socket.
In order to put more equipment, fan, computer, handphone, additional light or whatever, so you have 1, 2, 3, 4. Of course, this is in parallel arrangement. It doesn't cause extra current. But this is wrong. It's very dangerous. So one socket is meant for one equipment. This is the best. Not like this. It can be done because all are in series, but it's not safe. It's not safe. We never know it. Because when there are too many cables, there might be some faulty damage to the cable. Again, it's the same. Okay. Do not use damaged cable, plug or socket. Do not allow water to come near to the EE. Wear glove during handling intracardiac catheter. So glove has a high resistance, so when you're handling intracardiac or any procedure, please use glove. Okay, thank you. I think that's all. Any questions?